So one of the amazing things what Euclid did was he proved like there are infinitely many prime numbers. Okay? And the kind of the proof is simple, but it's really elegant. Okay? So let's just prove that theorems. And I really want you guys kind of memorize the statement and the proof too. Okay? Proofs is simple, but the statement is so powerful. Okay? So let's say this way. We want to prove there are infinitely many different prime numbers out there. And we want to use the contradiction method, which means let's assume that there are only finitely many of them. Okay? There are a finite number of primes only. Okay? So let's say that P1, P2, P3 up to PR is the only prime numbers. Right? So this is the set of all prime numbers. Okay? Then let's say choose a number which is multiple of those primes all together and adding one more there. Okay? Then clearly this is also an integer, especially the positive integer, right? So natural number. And by the fundamental theorem of arithmetic, this is an integer, positive integer, which means it has a prime factor, right? At least one of them. So by fundamental theorem of arithmetic, we can claim that, and hence it has a prime factorization, right? So it must has a prime factor, a prime divisor, which we don't know yet. So let's say P. Okay? Then we already assuming that this set is the set of all possible prime numbers. And by this, n has a prime factor, right? Like p is a divisor of n, right? Like that. And it's a prime number, which means this p must be one of these, right? We don't know which one. Okay? So we can claim that the p must be certain pk, right? The k is just index, so 1, 2, up to r, one of them. Okay? Then, because of this, right, we know that p is a divisor of n, and p is also a divisor of p1, p2, up to pr. Okay, because of this, right? P is one of these, so definitely is a divisor of any number multiplied by p itself over there. Right? Then one thing we checked at the beginning of this chapter was like I think it's 1402 F. So you don't need to write down, but we already have A is a divisor of B and B is a divisor of C, and A is a divisor of linear combination of it, right? But especially like B minus C or something like that, right? We have that. So let's just put these together. So we know P is a divisor of n, P is a divisor of that number. Therefore, then P must be divisor of subtraction of these, right? So n minus P1, P2 up to PR. Okay? Then P is a divisor of, what was n? This, right? Plus 1. So P1, P2 up to PR plus 1 minus P1, P2 up to PR, okay, all together. So we just cancel out these two. Remaining one is P is a divisor of 1. That is a contradiction, right? Because P is a prime, which means what? It must be at least 2, right? Or greater than 2. And cannot be a divisor of 1, right? Because the only divisor of 1 is 1 and negative 1, right? There is no other thing. So, no way. Then, all the arguments are just true, right? So, it was okay. So, how do we get this kind of wrong conclusion? Because at the beginning, we just assume that there are finitely many prime numbers without any reason so far, right? We just assume it. That's the only kind of missing part, right? Okay. We just accepting. So which means what? That assumption should be wrong. Okay. That's the reason to get the wrong conclusion. So we cannot accept it, which means what? If we don't accept it, there is only one result, right? There should be infinitely many prime numbers out there. Okay. So that's the end of proof. Then let's say if we have now like a we use very similar notations, but forget the previous theorem. Let's say this set is a set of distinct primes, only just up to r primes only, right? And the question is whether if we adding one more is a prime or not. So it sounds like, yeah, looks like why not? And even we use this notation in the previous proof, right? So be careful. Okay? That's the reason for this example. So like if we have like a 2 and 5, no one says we have to include every possible primes, right? Like 2, 3, you just choose anything. So if the collection of primes is like a 2 and 5, then if we multiply these 2 and adding 1 is 11, which is a prime, right? That's good. But how about 2 and 7? Then 2 times 7 plus 1 is 15, is not a prime, right? So if it's not true, right? This notation is a prime? No. In that case, in math, all we need is showing just the counterexample, right? So not this one. You just check and error style. So you just say since from this collection 2 and 7, the result of that equation is not a prime. So you just answering no. The answer is no, right? That's enough. Okay, so we just accept the fundamental theorem of arithmetic, like any prime number, any integer as a unique prime factorization. But we didn't check how, right? I believe you already know how to do that. But okay, so this is how it's going to work. And let me just use this Excel file because it's just simpler to show all the procedures. Okay, so let's say, how about factorization of 1234? Okay, then it says it's 2 times 617. That's all, right? So the procedure, to step by step, how we can do that. This is the actual procedure, right? Divide the given number by the smallest prime number, which is 2, right? And keep doing it. So it's a little bit difficult, right? You need to check everything, and that's why you need if you don't remember, then you have to need to find the prime factors of 617, right? How? What was the square root of 617? Is about 25. Do you remember 625 is 25 square, right? So that is close to 25, right? Less than 25. So which means in this case, all you need is just checking whether this number is multiple of 2, 3 up to 23, right? That's enough, right? So just check one by one and you can see there's no more factorization of factors of 617. Then we know the prime factorization of 1234 is 2 times 617. This means it's the powers, okay? So let's just change that number to find another one. How about 4321? In this case, once again, 29 times 149. Okay, so it's another kind of stuff, right? Then we need to check. So you can check this one. Let me change the one which is given in our study book. How about 2800 as the given number? Then it should be factored to 2 to the 4 times 5 squared times 7. So let's just check one by one. This is what you're supposed to do. Start from the smallest prime first. So try to divide 2800 by 2. The quotient is 1400. Of course, it's a factor, it's a divisor, so there is no remainder, right? So that's it. Then just try to take the division of this quotient by starting from smallest prime again, 2, right? So this is possible. Keep doing it, right? So up to this is all multiple of 2, so we got that much. But when you got this quotient, 175, 2 is not working anymore, right? Then go to the next smallest prime number, which is 3. So looking for whether this one can be divided by 3. It's not, okay? Because the sum of all the digits, if that is a multiple of 3, then the number itself is multiple of 3, right? There are certain rules out there, right? Okay, we don't have time for that, but so check it. So 3 is not going to be a factor of any of these actually, right? Numbers. Then go to the next one, which is 5, and definitely it's a multiple of 5. Then take the division, 35, which is still multiple of 5. So whenever you got the next case, you don't need to start from 2 or 3. You already checked everything, right? So after passing through 2, you don't need to check whether the quotients are multiple of 2's or not anymore, right? You just go to the next ones only, right? So we already know 3 is not a factor of 175, which means no matter what quotient you have, those are not multiple of 3 anymore, right? So kind of smallest possible factors of that case are just 5, right? So all you need is 5, 7, or something like that, right? 35 is a multiple of 5, and remaining is 7. Then as you can see here, 7 itself is a prime number, but it's kind of right after 5. Then that's the case we know, or we should stop there, right? So just keep doing it, then 1 is the 1, right? So altogether, the given number 2800 is equal to how many 4s? I mean, how many 2s? 4 of them, right? So 2 to the 4. And we have 2 5s, so 2 squared. And we have only 1 7, so 7 to the 1. Okay? So just collecting this one gives us the prime factorization of given number. Okay. So once again, these Excel files are just for checking method, right? And see how it's going to work. So please do these procedures by yourself, okay, whenever it's asked. Okay. So practice for that. So in written format, mine looks like this way, very similar to the Excel file. Put the 2800. The first possible factor is 2, so 1400, and 2, so 700. Divided by 2 is 350. Divided by 2 is 175. Then 3 is not working, so 5, so 35. 5 and 7, and we know this is prime, so then you can stop here. So you can write down 2800 is 2 to the 4th times 5 to 5 squared and 7. Okay?